Well, hello there. This is Dr. Keith Schubert. This is the second video lecture. We're going to be talking about, in this one for numerical scientific computing, we'll be talking about actually our floating point number system and where some of this stuff comes in, give you a brief overview of it, enough that you can kind of analyze and start thinking about how errors work and how other things go on. Let's start out by talking before we go into binary numbers about just regular scientific notation, because what we want to do is represent real numbers. Now when we're trying to represent real numbers, we're trying to represent something often for science problems, so we're dealing with problems of the form, let's say 1.23 times 10 to the 5 or whatever. Now this same thing, we recognize, okay, great, that's scientific notation. But this is exactly the same as if I had taken this and said 0.123. Now, by taking this and shifting it over one, I've made this smaller. To keep it the same size, I have to increase what's going on here. Now, these are identical numbers. And, we start thinking, okay, great, I want to be able to represent a number. Scientific notation gives me a way to represent things in a nice, intelligent manner. But something like this, once I go to programming a computer, if I have two ways of showing the exact same number, I'm wasting space in my computer. I should only allow one way and then use the extra space afforded by the bits of the system to represent more numbers. Reals are much larger than anything we're going to ever be able to represent inside a computer. There's more reals than there are integers. So we're already in trouble on that one, and we can't even represent all ins. So we're talking with a kind of a beast of a different kind here. So we don't want to be wasting things with them. So our first idea that we're going to do is we're going to disallow things of this sort, which means we're also going to disallow the other direction, 12.3 times 10 to the 4th. All right, that's also going to be disallowed. We're going to force you to have normalized numbers, which in base 10 means that the first digit to the left of the radix point is going to have to be non-zero. Now when this goes to binary, this creates a pretty nice little situation. Let's imagine we had a binary number, 1.0101 times, now our base is 2, times whatever, and we'll put in 101, right? Now, this is 5, but don't think I'm trying to say that's that. I'm just pick some numbers at random. Now, since we are saying this cannot be done by just shifting, we don't allow you to do 0.10101 times 2 to the 110. And so I'm not allowing you to do this. I'm requiring that first digit to be 1. Now this is kind of important. By saying it can't be 0, I'm requiring it to be 1. It will always be 1. If it's always 1, why should I store it? Again, it's a waste of a bit. I know it's always going to be 1 because I'm requiring you to normalize the numbers. So since I'm requiring you to normalize the numbers, I won't store that bit. We call it the hidden bit. So this is our hidden bit here, which means I only have to store this. This whole number here, right, this is called the mantissa or the significand. If you come from a more math background, you call this a mantissa. If you come from a computer science background, it's usually called a significand. But this is one of the things we're going to want to store, and of this, we're only going to store the part of it that is the fraction. That's this part over here. Now, in this particular case, if this was the most I could store in my system, I have a precision of 1, 2, 3, 4, 5, even though I only store 4 of the numbers. I only store the fraction. So this gives us an advantage. So we've already saved 2 things by intelligently choosing them. And this is kind of a big issue because in the past, prior to the IEEE standards, which came into effect in the 80s, every system made up their own floating point numbers. They were all different, and to be quite honest, most of them were pretty bad. Some of them had some good ideas, but a lot of times it just didn't work out so well. So what we've got once we've switched to the IEEE version, we've got nice consistent ones, took advantage of all of these properties. Now, you might think, wow, this is amazing. There's one disadvantage to doing this. How do you represent 0? 0 doesn't have any leading one. So we have to be able to deal with 0. So we've kind of got this whole 0 problem thing. So I have to have some way to encode 0. Other things I might want to deal with. In a sec, we'll take a look at the distribution of numbers, but that's going to lead us to something that we call the subnormals or denormals. And I'll show you where this comes in a sec, or denormal. We also have some problems that can come up here. We have to be able to deal with, plus or minus infinity. And we also have other conditions which we call not-a numbers. Say like, for instance, division by 0. There's also indeterminate forms. What do you do with 0 divided by 0? Or say infinity times 0. Things that essentially lead you to problems of, oh wow, I don't know what to do with this. There's other things. What if it can't be represented? For instance, square root of -1. Right? Or a log of -1. A lot of different ones is this. So there's a lot of different ones that go in that can be broken into different categories, indeterminants, ones that are actually complex, things of this sort. We could take the 1 over 0 and we could say, okay, great, we make that an infinity, but then you run into, all kinds of other funs once you get into them, the questions of, say, infinity minus infinity. What is it? So anyway, this gives you some idea of some of the issues we want to look at. Let me first take a look at this one. When I do this, I'll answer the 0 question as it comes in. Just to underscore this one, technically, we map up to here. So I'm just giving the things that aren't in our normal system special cases. So I really should note, 1 divided by 0 gives us plus infinity as far as we're concerned on here. But you could go a lot of different ways. I could also just say, hey, forget that and make it infinity down here. But we'll talk a little bit more about those in a sec. You can see my lovely alignment thing to make sure I know I'm staying inside the page. Okay, so let's come in and take a look at these. To do this, I'm going to consider a binary number system that's a little bit smaller than normal. So I'm going to have a precision of only 3. And that means that I've got a number that looks like 1.xx times 2 to an exponent. So I only need to store the fraction part, so I really only have these 2 digits here because I am dealing with normalized. And to keep it small again, because I have to draw it on a piece of paper, I'm going to have my exponent in the range of -1 to 1. Now, what I would like to do is draw my number line. Now, I'll put 0 in the middle because I have the ability to start off with plus or minus. So I'm just going to do the plus side, and the minus I will get reflexively. So we want to consider what's the smallest number I can get without having to deal. I haven't talked about 0 yet, but you'll see something cool here in a sec why I'm going to deal with it. Let's say that I wanted to deal with the smallest I could do with my normalized numbers. Well, the smallest I can ever have is xx is 0. So it's got to look like 1.00 something. Well, and as small as I can get on the exponent is to put 2 to the -1. 2 to the -1 is a half, so my smallest number is therefore at 1/2. Now, we can look through this and say, okay, great, what's all the other numbers that I have to deal with? Well, let's walk through each of these kind of different exponent ranges. If I had the smallest one, this is the smallest one with smallest exponent, I could also have 1.00 times 2 to the 0. That's the next exponent that I have in there. 2 to the 0 is 1, so that's just the number 1. And I can have 1.00 times 2 to the first, my largest exponent possible. It means its smallest number is 2. All right. Now, let's take a look for each of these little exponent ranges, when the exponent is equal to -1, what's the biggest number I can encode when the exponent's -1? So that means I have 1.11 times 2 to the -1. Now, we take this number right here, 111 is 7, and the point with 2 places here gives me a quarter, and another one an 8, so I have 7/8. So the biggest number that I can get in the smallest range of my exponents is 7/8. You can see nicely that all the numbers within a particular exponent range fall just before the next exponent range runs. And you will find out that when we take a look at the same thing for this one, it will stop just before I hit 2, and they'll pick up. So each one of these is kind of defining a region of my number line that they're going through. Now let's get all the points that are in here. I've got 2 bits that I can select, which gives me 4 numbers in that area. And my 4 numbers, each one does, I can initially start with 0, 0, which gives me a half. I can then add just a 1, which is a quarter. A quarter times a half gives me an eighth. So each time I increase by 1, I'm adding an eighth, which means I've got these nice evenly spaced ones that are 5/8 and 6/8. 6/8 you could obviously reduce to 3/4. I'm just leaving them in eighths just so we can think of them in that way. So I really have 4/8, 5/8, 6/8, 7/8. That's how we are counting them. Because if you think about it, I've got 1, 0, 0. Right, that's my 4. 1, 0, 1. That's 5. 1, 1, 0. That's 6. And of course, again, it's 0.00 times 2 to the -1, which is an eighth. Okay, so now we can move to the next range. The largest one I can get for that one, again, it's the same pattern, 1.11, except now it's times 2 to the 0. So this is again 7, but now I just have fourths. So 7/4 is 1 3/4. So that's 1.75, 1 3/4. And again, you can notice on each one of these as I go, and I'm starting off at 1, going up to 1.75 in this range, and each one is just adding a quarter. So I've got 1, I've got 1 1/4, I've got 1 1/2, and 1.75. Now I want you to notice something. Because these exponents are changing, it's changing how big the step size is. So in the range under 1, from a half to 1, the step size, or the distance between points, is an eighth. From 1 to 2, the distance between them is a quarter. When I go from 2 on up, guess what that step size is going to be? Well, let's find out. Our biggest number will be 1.11 times 2 to the first. Right? So that really means I've got 7, and I've got a quarter times 2 halves. So that's 7 halves. That's 3.5. So 2, 3, 4, 3.5 is right there. And so I'm now going from 2 to 3.5, a bigger range. And each time I add 1, I'm adding 1 here, but since it's times 2, I'm really just adding a half, a quarter times 2. So each of these are going by half. So I've got 2, 2.5, 3, and 3.5. So now each one of these has a spacing between points of a half. So you can see as I get closer and closer towards 0, I'm getting smaller and smaller. As I'm getting further away, I've got bigger ones, right? An eighth, a quarter, a half. If this would kept on going, obviously I'd have 1, and so on and so forth. Now, how small these steps are depends on how many bits I have over here. Now, that's an important feature. It's actually shows you what we call machine epsilon, the smallest bit that's in here that I can represent. If you notice, 1 is my smallest, and the distance between the smallest and the next smallest, so in this case it's 1, in my system it's 1.00 to 1.01, is just that bit in the last area. How big that number is when we take a look at it at the unit scale, taking a look at size 1, is what we call machine precision, and that tells you how accurate your system is. I want you to notice a couple other things that are in here. Notice I got this nice fine area of 1/8, but it runs from 1/2 to just under 1. Right around 0, I've got this big blank area that is significantly larger than my points. This is kind of a big null space. And if you realize once I have this negative zone, I would have -1/2. Right, and I've got 1, and oops, I should have only had 1, 2, 3 in between there. Right, it's 4 when you count that. 1, and then I have 1, 2, 3, 4, going up to -2. Right, so on and so forth. You have this big region that has nothing in it. And this is where we're going to stick our 0. And this is where we want to put our subnormals. So we don't want to leave this big blank zone, and it's as I get closer I'm getting finer and finer precision, and then all of a sudden it disappears, and it's a really wide spot. I realize this zone right here is a total width of 1, from -1/2 to 1/2, significantly bigger than your 1/8 here. So what we do is take this one and we divide it up into pieces. And we have another range. This is why we only let it go to -1, because we'll encode this if we use the next one down, -2, as an exponent. What we would say is that one is our denormals. We won't treat it as a normal equation. We just allow it to be 0.xx. And then we've got our number system off of here. Okay, and this one going up, we can nicely divide it, and you can fit your numbers in the range, and you've got plus or minus, so you can bet both sides. This also allows us to do 0.00. That allows me to get 0. Not only can I get 0, but since it's plus or minus, I can also have plus or minus 0. Which has its disadvantage, but it also can be useful in some of the areas, particularly with limiting arguments. You can end up with plus 0 when you come from this side. You can end up minus 0 from this side. So that gives you an ability to also kind of tell where it came from. It's kind of a little bit of a waste, but there's no efficient way to deal with it otherwise. Alright, so this gives you a little bit of an idea of how the numbers are kind of spread around. Now, when we go to IEEE, and I go to single or double precision or any of the newer ones that came out, you obviously have a lot more bits than what I'm showing in here, because it would be very hard to draw. Indeed, actually, if you go to double precision, for instance, I've got 53 bits of precision, which means I store 52 in the normalized format. If I'm dealing with single precision, I've got 23 bits of precision, and in that one I store 22 of them. It just, gives me a very nice area of storage on them. So I've got, 53 bits down to 52, or 24 down to 23. I think I might have said that wrong the first time. But I've got 24 bits precision, 23 in single precision, 53 bits precision, 52 stored if I am dealing with double. That's a lot of bits. Now, if we take a look at those epsilons for it, and I'm taking epsilon to be equal to, in this case, 2 to the minus 23rd power, that's going on, you get around 10 to the minus 7th. Alright, so we call that 7 decimal digits of accuracy for a single precision number. If I'm dealing with epsilon for double, that was for single, this is for double, then I've got my 2 to the minus 53, and that gives me about 10 to the minus 16. So we say you have 16 decimal digits of accuracy. Alright, so that gives me my numbers as we go on. And we say, okay, wonderful. And we think, oh, it's easy, I can do it. I get 7 digits accuracy is huge if you think about for decimal stuff. Alright, we can't even measure that precise. Therefore, it must be all I need and more. Well, sadly, it's not all you need and more. I have a cute little example that I show online. Maybe we'll do this in class as well. which kind of demonstrates this. But let me walk you through the idea of it, and you are welcome to then try it, and I encourage you to try it on your own. Let's consider that I take a variable x, and into my variable x I'm going to stick the value of pi. Now the easiest way that you can get pi inside this, inside any programming language, is doing 4 times the arctangent of 1. So I just put that as a side note to you. If you think about what I'm trying to accomplish in this, when you've got your tangent of an angle and your angle is equal to pi over 4, that leaves your x and your y are both equal to each other. Right, so if this is x and this is y, at pi over 4, x equals y. So the ratio, which is what gives you the tangent, would just give you 1. So the arctangent of when they're equal times 4 would give you pi, because that arctan of 1 should give you pi over 4 times 4 gives you pi. So anyway, this formula here will give you pi to as many digits as the computer can represent. So don't just put in some small amount of pi on your own. Get the full value as accurate as your machine can hold it. Now what I'm going to do is I'm going to calculate an intermediate value of y. And what I would like to do is to take y, and I'm going to take a repeated square root. Right? So I'd like to take the square root of x 53 times. I'm assuming you're using double precision, so the square root 53 times. You can do this with POW. You have to do 2 to the 53, so you kind of have to do POW twice. Then what I'm going to do, so this will keep getting closer and closer to 1, because that square roots always shrink things towards 1. It's a contraction mapping. Then what I'm going to do is I'm going to undo what I did. I'm going to square it 53 times, and I'll stick that into z. Now, as a human being, I can look at this and I can go, well, all I've got is, squaring 53 times, square rooting 53 times, cancel. So what I should have in z is pi. So ideally, z equals pi. Of course it doesn't, because I'm giving you an example of where things can go catastrophically wrong. If you actually look at it, z is equal to e, to every digit of precision inside the computer. People kind of look at that and they go, whoa. And this is partially because the actual formula when you're doing this ends up being a way you can calculate e. You end up with 1 plus some little tiny number, and you're raising it to a power, and that's essentially the formula for how you calculate e. Now, without knowing things and kind of being a little bit naive, you can end up getting something. If you saw e to every digit of precision inside your machine, you'd be like, that number is e. But the number should be pi if I was actually keeping full precision everywhere. So this is something that as soon as you go to finite precision, and I can put in whatever precision number you have here, which represents how many digits you have, essentially I can make anything you do look foolish. So the goal of this is to just make you realize, hey look, I've got to think when I am implementing stuff. And sometimes more digits don't buy you anything. So there are quite a few times it does buy you a lot though. Now let me talk one more thing on here about some interesting stuff that can go on inside of numbers and when we're doing calculating, and then we'll talk a little bit about knotted numbers and things of that sort. Let's consider one more thing. Consider the classic parabolic equation, or parabolas, right? Ax squared plus bx plus c equals 0. And I want to find the roots of this equation. Now most people probably know the classic formula. X is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Now this is one way you could have completed the square. I could have completed the square. That kind of finishes it to this side. I could have actually done the complete the square on this side, treating my units as it, and then gone them the other way. If you find your roots that way, you would actually get that this is equal to almost the kind of flip of this. And it's an amazingly similar looking formula as it goes on. The top and bottom have just flipped, and then 2A, 2C. Now, you may look at them, they're mathematically, they calculate exactly the same as a human being. You put them in, you will get the same exact answers. The funny thing is, they don't give you the same exact answers if you actually calculate stuff inside of your computer. So let's take a look at an example for this. Assume for a sec, just for simplicity and things like that, I'm going to only assume I have 4 bits of precision. Alright, so that's, 1.xxx as it goes on. Now, assuming I have 4 bits of precision that's going on here, I'm going to do this in decimal because, I'm a human being, and 4 bits of precision I can do as a human being if I need to, but it's a lot easier for me in decimal. So let's consider what's going on. Let's say I start off with A is equal to 1 over 200, and B is equal to 1, and C is equal to 1 over 200. You might wonder, how do I come up with these numbers? I came up with these numbers by picking in advance what I want the answer to be. I would like my roots to be x plus 200 times x plus 1/200th. And then if I took this and I multiplied by 1 over 200, I set that as my equation. If you multiply them all out, you end up with 1 over 200 times x squared. And when I multiply here to here, I get my cancellation as it goes in. Actually 200, and I get this one. So I'll get 200 plus 1/200th divided by 200, so I get my cancellations. I get 1, and then I have a 1 plus 1/200 squared, which is way too small to be represented in 4 bits. So I just end up with 1. This is a truncation error that comes in. 1 times x plus, and then I get the cross 200 times 1/200th, and then times a 200th. So I end up with 1 over 200. So that gives me those coefficients. And remember, this is not just approximately 1. Since it's 4 bits of precision, it truncated, it's gone. You lost it forever. As far as the computer knows, that's exactly what it is. Now, if I take and stick into these equations here, what you'll end up with, let me kind of do this in 2 pieces since they both share the common top and bottom. If I take a look at minus b plus or minus the square root of b squared minus 4ac square root. If I take a look at that, your minus b is just going to be minus 1. So that's a pretty simple one to take a look at. When I take a look at b squared minus 4ac, what you're going to end up with is something pretty darn close to 1, because I end up with 1 minus, and then I've got the 1 over 200, 1 over 200 times 4. Now, this is a small number to be sure, but I end up with 1 over 100 times 1 over 100, if you think about it that way, which means it's just at the edge of my representable space. Right? 1 over 10,000. So it's right at that edge. When I take the square root, I end up with getting just a little bit below 1. I end up with 0.9999. It's just exactly the last space that little difference pops in. So that's how I'm able to pick it. I picked it for a reason, and the reason why I picked these particular numbers, now that if you look at it, if I get the minus term, right, so I got minus 1 minus that, I end up with minus 1.9999. The 9 will cancel out, it'll round this up, so in 4 bits I'll get minus 2. If I took the plus term, then what you're going to end up with is minus 1 plus that, I'll end up with 0.0001. But the rounding that had happened in there is going to cause this to be, these digits down here become significant, but they were lost. So I'm wrong. This is not exactly the right answer. But it's all I could have calculated inside my machine. So I'm kind of stuck with it. And so this is going to underscore thing. This one is perfectly fine, and this one is really bad. And it's all from this term up here. So we would like to be able to use this term. We'd like to not use this term. All right, so let me put this in the top one. So first off, I've got my minus 2, and I've got my minus 0.0001 term that goes on. So if I had stuck, so I'm going to make a little table here based on my two different formulas. So this will be this equation with the minus 2 term, or the minus 2 root that comes in, or minus 2, I should say, the top part. So this is minus 2 on the top. That means it's minus 2 on the bottom. All right, and the minus 0.001 is this value on top, 0.001, and on the bottom it's minus 0.001. Okay? Now, what goes on top or bottom is 2a or 2c, and in this case, a and c are the same thing. If I double them, I get 1 over 100. So in this case, I get the number 0.01. Alright, so if we look at what we get here now, when I take minus 2 divided by 100th, that gives me here, in this first kind of square of it, I'll write this. This is kind of calculating them out, the minus 2 one, the minus 0.0001, and this is your traditional way, and this is kind of the new way that I gave you to formulate them. When you calculate minus 2 divided by 100th, you get minus 200. Now, that's exactly right, because minus 200, x equals minus 200, means it's x plus 200. So, it says a note, x equals minus 200. Taking the minus 200 to the other side is x plus 200 equals 0. So that is the root. All right, now we had picked that. So this one has perfectly calculated one of the roots. All right, from this formula using the minus 2. Let's take a look at the minus 0.001 term. I get 0.001 divided by 0.01. What that ends up giving me, right, I'm in essence shifting over, and I end up with 100th. Right? Now, if you think about this, that means this corresponds to x plus 0.01. But that's x plus 100th. I should have gotten x plus 1/200th. So this is off by a factor of 2. It's twice as big as it should be in magnitude. This is really bad. This one's good. Let's take a look at our new formulas. I've got 100th divided by minus 2. That's minus 0.00. Oops, that's kind of ugly. 005. Or minus a 200th. X equals minus 1/200th means take it to the other side. X plus 1/200th equals 0. X plus 1/200th, that's my root. So this one checked out wonderfully. Let's take a look at this one and see if it works well. 100th divided by a 10,000ths negative gives me minus 100. It's supposed to be minus 200. It got minus 100. That's horribly bad. Again, a factor of 2 off. If you think about it, most people, you go, oh, 0.01 to 0.005 doesn't seem like much to us, but minus 100 to minus 200, that's huge. Now, if you notice, it's always on this side I did bad, and it's always on this side I did good. Right? As long as I don't have this cancellation going on, I got the term that added to it, it worked well. When I had the term that canceled, the signs were opposite, that's when I did poorly, because that's when I lost precision and I just bumped into those terms that disappeared when they shouldn't have. So the underscoring message of this one is, when you're looking at things, we want to look at issues like cancellations that happen inside a calculation. And when we start running into problems, like if you're using the traditional one and you run into a problem finding that root, sometimes alternate formulations can end up giving us a perfect method. We can actually get both roots for a quadratic extremely accurately, but we have to calculate one with this equation and one with that equation. And we even know which one to calculate. You always take the one where the signs are in the same direction. And you do it for both equations, and you will get the root extremely accurately. So if you don't know that and you don't do things, you will make naive mistakes. And this is part of what we want to talk about. And it turns out there's only a few of these type of problems that exist. There's standard kind of general rules, so once you start getting familiar with them, you can start watching out for them. All right, let's talk about kind of our final things that I would like to go over here, which is really talking about the issues with knotted numbers and the infinities and things like this. These are special codes that go out there. Now the question a lot of people ask is, why do I want these codes? Why not just give me, as many numbers as you could? We're actually going to take the largest exponent, and we drop it off. You can't encode numbers. We're just going to allow the significant to encode special cases. Now, people look at that and they go, oh my goodness, that's a lot of bits we're pulling out and wasting. Yeah, I mean, all the significant for that is being used just to encode these special cases. I agree, it's big, but it's for a very good reason. And the reason is completeness. We want our system to be complete, which means that if I go to calculate something, there's always a number in the system that is correct. Right? So if I go to do some operation, some f of x, I want to know that this is well defined. Well, there are some cases like, square root of -1, where if I'm dealing with reals, what's that defined as? Well, for us, it's defined as not a number. Now, the reason why this is so important is my system doesn't have to crash. And inside that not a number, I can encode the information that, hey, you did a square root of -1. So I can either allow this to signal or not signal, which means do I throw you something? So we can allow it to signal or not signal. And not signaling is called quiet. So we often call this signaling or quiet as it goes on. So they're called signaling not a numbers or quiet not a numbers. And you get all the codes for both of them. And do you want to be told about it? Do you want to have to look it up yourself to see if something happens? And beyond just -1, like I said, we've got ones for all kinds of the different things. This is a case where we end up with areas where you get a complex number, but what do you do with 0 over 0 and that kinds of stuff? These ones become, not a numbers that are, hey, I don't know what it is. It's undefined as it goes. Infinity minus infinity, all this kinds of fun stuff. So all of those ones that are not a numbers are there. Now, how do you handle these not a numbers? Now, this is a big issue of argument that's out there. And it's been a long-standing position within the numerics community that really, we should not cause programs to exit for things like division by 0 with a decent floating point system. Now, the reason is it's something we can signal, the computer programmer can fix, and can move on from it. right, so that the program does not have to crash. There's an awful lot of systems whose default behavior is you run into a problem and they crash. There's no reason to. We included all these things so you don't have to crash, so that you can find out what it was and you can fix it. You can handle the problem. And you might think, well, why would I want to fix this? Well, consider a particular case. A few years ago, there was a naval vessel, I believe it was a cruiser, a missile cruiser that was off the Virginia coast, and in an unimportant system, somebody had left a field blank in one of the databases, and when that got run and they used that blank field became a 0, and it ended up being a field that was going to do a division, so they had division by 0. Because the people who did the programming did not actually handle things using our signaling, and like I said, not a number is not there. We actually have infinity codes, and it should have gone in infinity code, and it should have just quietly handled that, and the code could have been notified, and away we went, and it would have been simple. But what happened was, since that didn't go, that program crashed. When that crashed, it took down the OS. When it took down the OS, it took down the cruiser. I mean, believe it or not, for about 4 hours, this thing was seen dead in the water. It couldn't run its engines. They were run computer controlled. So this whole ship was sitting there dead in the water, unable to do anything while they tried to get the system back up again. Because when it crashed hard, and this type of stuff should not happen. It also turns out this exact same thing back in the late 90s, the European Space Agency was making the Ariane 5 rocket, which is their rocket they use to, lift things into space and, good stuff. And it was carrying, a scientific mission and things of that sort. And shortly after takeoff, they got a division by 0. It crashed their system. It stopped taking data, and the rocket ended up spinning round and round and then blowing up. Billions of dollars of scientific equipment and scientific data was just lost because somebody did not just handle this the correct way, which is allowing it to continue running, and you can actually, at that point, recover. You can do all kinds of fun things because we tell you what happened. So this is, it may sound like I'm kind of beating a dead horse on this, and maybe I am, but these things are not without consequence. Billions of dollars, lives, national security, all kinds of stuff get messed up because people do not code things well. So you want to make sure you take advantage. These are not some little side freaky thing inside your numbering system. These are very important ones to keep your code running. The knotted numbers and the plus and minus infinities. They give you a complete number system, so that even when you start getting errors like you get too small and you underflow and things go to 0 and all the rest of this, everything handles at least according to a set of rules that does not ever require you to crash. And we can't guarantee you will always get the perfect right answer, but we can at least tell you when things go bad, and you can handle it inside the code without having a need to end a program. So this is the importance of the signaling and the not signaling. You choose signaling or not signaling of whether or not you want to be alerted to this, a signaling error or a quiet error. As you go on, how important is it to know about it that instant? Are you planning on looking it back up? Things of this sort. So, in any case, that's kind of my soapbox for this video. I hope it's helped you a little bit as you're going through. Just as kind of a recap on things, what we are dealing with is situations where we've got scientific notation numbers. We are assuming for most of our cases what we call the normalized numbers, something that looks like 1.xxx as it goes on, times 2 to the exponent. Some people do wonder, maybe before I go, I'll give you one kind of little insight into why they pick the thing they do. Technically speaking, inside of IEEE, they have -1 to the sign bit times this whole lovely thing here of going on, and the exponent is kind of stored in an oddball way. And then when they come in here, you store your sign bit, and then you store your exponent in what's called an XS code, where you do XS, and then you add in for double precisions, it's 1023, and then you have the fractional part of the significand that gets stored there. So this is the order that it gets stored in. People wonder, why do you pick this particular order in this odd numbering system? The reason is, your biggest thing of telling you want to do is usually to compare two numbers to each other. The biggest thing that will tell you what it is actually this sign bit. If it's a positive number versus a negative number, it doesn't matter what anything else is. If the sign's different between the two numbers, all you have to do is look at the sign bit. So if the signs are different, it allows me to instantly compare them looking at just one number. The excess code also allows me to do this change quickly. Normal way we handle things inside of encoding integers, where we use 2's complement, actually puts the negative numbers as larger than the positive numbers. And all you have to do is just consider for a sec just a small version of this. 0, 0, just consider a 2-bit version. If I just had a 1-bit 2's complement, that's going on. This would be the number 0, this would be the number 1, and then now you come in here, this is -1, and then I should try to make those look like equal signs, and this is -2. So that would be 2's complement for a 2-bit number. Now if you think about this one for a sec, this is normally what we consider increasing, and so our number goes 0, 1, -2, -1. -1 is our biggest number. So when I'm doing comparison, I'd like to start looking at each bit and walking down. The excess codes, and in this case we would have an excess, I could do an excess 1 or 2 code for it, and I would just shift it up. Assuming I did an excess 1 code, which would be a 2-bit version that would be used for IEEE type standards, that 3 there, done excess 1, is encoding the number 2, 1, 0, -1. And that would be my encoding system. If you notice, they get strictly bigger as I get bigger. So now I can do a comparison bit by bit without having to undecode the number and do all kinds of fancy computations. So I can now do size comparisons, and then the fraction is the final and least significant one. So it was all added for a very good and intelligent reason as you went through. I'm only hitting this one lightly because this is covered in earlier courses. This is just a refresher, and this is kind of something that's particularly important to us, so I want to make sure you remember it. So anyway, I hope this helps, and we will see you in class. Have a good day.